Okay, so for today's class, the plan is to continue our discussion about the goodness of fit for generalized linear model, and also how do we do inference for the model parameter, the beta coefficient vector we're interested in. But before we come back to the track to continue our last lecture, I just want to deviate a little bit to discuss the multiple tests we can do for generalized linear model. So specifically, I would say there are several ideas we want to do. So I will say there are three different ideas for this generalized linear model. Let's say we have this G, okay, let me just write it again. So Yi independently following a distribution F. I'll just put mu I with some other parameter phi here, but we are particularly interested in the mu I. And so then we try to link mu I to our covariates. That's what we want to do. So this is the random structure. This is the systematic structure. So therefore, you see that if we want to test whether this beta is zero, if we're interested in this question, is beta zero? There are three possible ways to think about the problem. So I think this will actually talk about some of the later contents we'll cover today, which is inference about beta, but let's just do it first. So there are three ideas. And then I would say this is like my summary after covering or after reading these things and try to teach this class for several times. I think I gradually came to this thing about simplifying these various tests under the three ideas. So the first one is based on estimator of beta. So directly work on beta hat, which is what we obtain from the optimization. And the idea is that if this beta hat is somewhat close to zero, we think this null hypothesis is more likely true. If this beta hat is very different from zero, we will more likely reject the null hypothesis. That's the intuition. But of course, we must consider the variance of beta hat itself, right? Because the larger the variance, the less certainty, less confidence we have for our decision. So we're in general less likely to reject the null, because with a large variance, even though beta hat is far away from zero, but still it's possible that beta is zero. So therefore, considering the variance is very important. And the Wald test is specifically designed for this. So Wald test is basically a normalized squared version of this beta hat. So this gives us the Wald test. And if beta hat is one-dimensional, or beta is one-dimensional, then it's actually simpler. The Wald statistic is basically this formula. Beta hat minus the value beta takes under the null. Okay, so here it's zero, but maybe we can write it more generally, say, or more generally, the null hypothesis is that beta is a specified value, say beta zero. Let's use this as the more general form. So in this case, the Wald statistic will be beta hat minus beta zero squared divided by the variance of beta hat. And in many cases, we don't have the variance known because the variance may involve some other parameters. So in that case, like the sigma square in linear model, we will plug in those parameters, then this variance, if involves other parameters, will become variance hat. Okay, so we may need to put a hat on the variance as well. That's the one-dimensional Wald statistic. But if beta is multiple parameters, it's a vector itself, then it's the RP. If that's the case, then essentially the Wald statistic is what? It's basically this. beta hat minus beta 0 transpose times the inverse of the variance covariance matrix of beta hat. Okay. We may have hat for the variance, but we'll take the inverse and then times beta hat minus beta 0. So in this case, we are going to normalize this square form by the variance inverse. So you see, this is like the one-dimensional version, and this is the multi-dimensional version. But the idea is to work on beta hat and use it for testing the null hypothesis. That's the first idea. Okay. And then the second idea is based on likelihood. So the likelihood, we can write it as, or maybe just use big L, likelihood of beta. We work on this. And we will have two maximum likelihoods. One based on what? The null model. Under H0, we have this beta set to beta 0. And there are potentially other parameters we need to estimate by maximizing this constraint or restraint likelihood, so sigma squared. We maximize that, plug it in. And then we will have another likelihood under the alternative, which is not this constraint. So in that case, we are going to compare this L beta 0 versus L beta hat MLE. So this is like the unconstrained MLE under the alternative H1, alternative hypothesis. So working on the two likelihoods, the idea is that if they are close to each other, which means that the unconstrained model is similar to the constrained null model, then the null hypothesis is likely to hold. So this is like a very general approach to test this null hypothesis. Then in this case, the statistic, which we call the likelihood statistic, likelihood ratio statistic, so this is commonly referred to as the LRT statistic. If you see people use this term, it's referring to this statistic defined as -2 times the log of the ratio with the constrained likelihood as the numerator and the unconstrained likelihood as the denominator. Okay, one thing I forgot to say, okay, is here. Asymptotically, under the null hypothesis, this under H0 will converge in distribution, this W statistic. The distribution will get closer and closer under the null hypothesis that the beta is beta 0. And when the sample size is large, that's what we mean by asymptotically, to a chi-square distribution with p degrees of freedom. And p is the dimension of beta. So this is what we have for Wald statistic. For likelihood ratio test statistic, this one, we can also show that asymptotically for most of the cases. For most of the cases, like we have to rule out the thing that, okay, the beta 0 happens at a boundary of the domain of beta. So if there's a boundary thing, then we should be careful. But for most cases, if there's no boundary, like beta is RP, it's the whole real space, then there's no boundary thing. So don't worry about that. But we'll revisit this later for the more specific things. So it will converge in distribution under the null hypothesis also to chi-square p dimension, chi-square p degrees of freedom. So this p is the difference in the degrees of freedom between the two models, the alternative model, no constraint, and the null model, where we constrain p parameters to be beta 0. So the second idea is likelihood ratio. Okay, and the third idea, which we didn't talk about, but I hope to introduce today, is to focus on the score S beta. if you remember, what's the definition of the score? It's defined as the gradient of the log likelihood. So it's defined as this. How do we write it? It's the gradient. So basically, using our previous notation, we will just use this. Okay, log likelihood of beta, we take the gradient. So you know, like this score is itself p-dimensional. So the score test will work on the score function. And you know, the score function would be a random vector itself. Recall that because it will involve the random variables which are involved in the likelihood computation. So score is itself a random vector. So the idea is that the score itself would be, if the null model is correct, if we have the beta 0 as the true value of beta, then the score at beta 0 would be equal to 0. That's the thing. But we also understand that the score is a random vector. So therefore, it wouldn't be exactly 0. So similar to this beta hat argument, if it's not exactly to 0, whether we believe the null model or not, it will depend on the variance of the score. And we know that the variance of the score is Fisher information. That's something we covered when we derived the like IRLS. So then we introduce the Fisher information. We call that I beta. And if you remember, this is basically the Hessian of the log likelihood with the expectation. So it's expectation of the Hessian of the likelihood, log likelihood at beta. And this is P by P. Okay, that's the Fisher information. So then the score statistic is defined as this form, very similar to the Wald statistic here. So it's defined as S at, let me just put it this way. It's defined as S under beta 0, under the null hypothesis. Fisher information under the null hypothesis, we take the inverse, and I should have a transpose here for the score vector times the score at this. So we need to compute this. And there might be some other parameters you need to estimate besides beta, such as the sigma square in linear model. And usually in statistics, we call those nuisance parameter, which means that they're not the parameter of your primary interest, but they must be estimated. So then these parameters will be estimated by maximizing the likelihood under the null model. So beta is set to beta 0, but we maximize the remaining parameters by maximizing their likelihood. So then putting them together, we get a score, Fisher information inverse score. And this one is called a score statistic. And this one is known to also convert to chi-square with p degrees of freedom under the H0. So these are the three major ideas in the field. And so far, we have introduced the first two, but not the third one. So you will see the third one used in some literature. But the good thing about them is that they are shown to be asymptotically equivalent to each other, which means that if you have a very large sample size, then it doesn't matter which one you choose. They follow the same null distribution and you will reach the same rejection decision. But practically, so I would say 1, 2, 3 asymptotically equivalent. And I would say this is like the major research direction before the 80s in mathematical statistics. So at that time, the statisticians who work on theory are trying to understand these different test statistics, their power and their restrictions, and whether whether they lead to the same power, or I mean, whether they're equally powerful or which one is more powerful. So these are the popular topics back then. But the good thing is that they are asymptotic equivalent. So you may wonder, in practice, do I really care which one to use? And there are some practical advantages why people might choose score statistic over likelihood statistic in some cases. The reason is that in likelihood ratio test statistic, you need to fit two models, one for the null model, one for the alternative model, then you compare the two. But for the score test statistic, you only need to fit one model under the null. So you save the model fitting for the alternative. And this could be advantageous, especially when your alternative model fitting is a computationally intensive problem. Okay, so this is only fitting the model under H0 only. Okay, but for the likelihood ratio, you need to fitting two models separately under H0 and H1. That's what you'll need for likelihood ratio statistic. And actually, if you think about this this Wald test, right? So for the Wald test thing, you are fitting the model under what? You are fitting the model under the alternative model, under the full model, right? So that's how we get the beta hat. Fitting model under H1. Okay. So you see that it's actually practically you do the model fitting in different ways. And similar to the likelihood ratio thing, there is another thing we talked about and we use in the homework, which is ANOVA, if you remember. On a side note, right? ANOVA is a different perspective in which you try to decompose this thing, yi minus y bar squared. You try to decompose the variability among your yi's, the n responses, into terms explained by your model. Yi hat minus y bar squared. For linear model, they share the same average. So the average of y1 to yn is the same as the average of y1 hat to yn hat. And the residuals. So in ANOVA, what we are looking at is how much variance is explained by this term, whether it's significant compared to this term, because this term is the variance explained by the residuals. So if this one clearly explains more than this one, we think the model, the model part is meaningful. Okay, so that's translated to, we believe that beta is not zero. For linear model, that's the case. But this ANOVA idea can be more generalized into the thing called variance component test. So this is like orthogonal to what we cover here, because it's not specifically focusing on beta per se, because you see here we have the estimator for beta, likelihood for beta, score for beta. So we concentrate on beta. But when we talk about this variance decomposition, we focus on the variance explained by the model. It's more general. I would say it's not specific to the form of beta. So later in this class, once we talk about some linear mixed effect model, when we have the linear model with fixed effects and random effects, this will be more relevant. Because so far, all the model explained, we consider the covariates to have fixed effects. By fixed effects, we mean that the beta is considered to be a constant vector instead of a random vector. But later, we'll talk about random effects later. So then once we are there, then we will revisit this topic. Okay, so for now, I just want to introduce these ideas so you know they are out there. And practically, which one would you choose? It's for I think the consideration is related to whether it's easy to do the optimization when you estimate the parameters, because you have to fit the model. Okay, so that's all. And then let's come back to the goodness of fit statistics. So let's say that the goodness of fit for test statistics for GLM, generalized linear model. So the first one we introduced last time is the deviance, which is exactly the likelihood ratio test statistic. Okay, but here we are basically comparing two models. So it's -2 times the log of the likelihood ratio. And the smaller model, the more constrained model we consider here is the GLM. Okay, let me just put it this way. Mu hat GLM. And the unconstrained likelihood is the mu hat under the saturated model. So then what is the mu hat? First, we define mu as the expectation of y. Okay, it's a vector, n-dimensional. So it's basically expectation of y1 to expectation of yn. The expectation of the n responses, which is to be explained by our model, by the GLM model. So just to make it simple, that everything the model can tell us about y1 to yn is through this mu. Besides the mu, the randomness described by the random structure is the thing we cannot capture. So even though we assume the form to be exponential family, but we cannot really know exactly the randomness. So we can only try to capture the mean. So that means when we get a new data set with covariates only, no y, then to predict the y's, we will use the mu. We will use the model parameters, the systematic part, to do the prediction. But for the random part, there's no control for us. So that's the high level understanding of what GLM is doing. But given this mu as a vector, n-dimensional vector, we estimate it in two ways. So maybe we just write it as mu1 to mu_n. Okay, write down the components. So for GLM, right? For GLM, what is mu_i? We actually estimated mu_i hat as the inverse of the link function of xi times beta hat, xi transpose beta hat. That's it. Because the output of the GLM will be beta hat, the coefficient estimates. Then we can use the covariates, do the inner product, linear function of the covariates, inner product with beta hat. This is that we call the linear predictor. But for GLM, if it's not linear model, then this is not mu_i hat directly. We have to use the link function inverse transformation. The reason is that we assume G mu_i is xi transpose beta. That's the reason. That's the mu_i hat we get from GLM. From the saturated model, we have mu_i hat just as yi, because we have one mean parameter per observation. Then in this case, the best guess is to use yi to estimate mu_i, to estimate mu_i. Okay, do we have any questions here? So you see the model complexity is different. So the GLM has P parameters in the beta, while the saturated model has N parameters, mu1 to mu_n. So there's no constraint, no linkage among them. They are just, each of them can vary freely while in this case, we have the beta to tie things together. So basically for all the n observations, they share the same beta, and their difference is only in their xi, only in their covariance. And the covariance determine their mu I. Okay, so with this, then I think last time I gave you the log likelihood of the group data logistic regression, right? That's where we stopped last time. Let me try to grab the notes. So this is where we have last time, the end of last lecture. Here, we wrote the log likelihood of mu as blah, blah, blah. So you see, it's the summation of yi times log mu I plus ni minus yi times log ni minus mu I plus some constant. So the constant can be ignored because they have nothing to do with mu I. So for this case, if this is the log likelihood we work on, then we need to know what is the mu I hat for linear model, for generalized linear model, for logistic regression. What is the mu I hat for saturated model? That's yi. So that's what we already know. So then for this model, I'll just continue here. So for the group data, logistic regression, for this, then we have mu I hat GLM from what? So here the mu I is defined as n times yi hat, right? So it's actually ni times y pi I hat, because it's group data, and the group size for group I is ni. And we know what is the formula for pi I hat. It's once you get a beta hat, it's basically exponential xi transpose beta hat divided by 1 plus exponential xi transpose beta hat. So this is the probability estimates from logistic regression. Okay, so then with this is your mu I hat GLM. And then what you do is that you plug this in, you plug it back in using this form. So what I'm saying here is that the deviance, so then the deviance, so with this, then the deviance is basically -2 times the log likelihood. I'm just writing the log likelihood here, mu hat GLM minus log likelihood mu hat saturated model. Okay, yeah, there's a question.
Yeah, could you just say once more what the saturated model means?
The saturated model is that you have n observations and you have n parameters. So if you use the linear model as an analogy, or for the special case, it's just interpolation. So it's just interpolation. So basically your line, or in that case, I shouldn't say a line. So basically you're just predicting every yi by itself. Since the number of parameters is equal to the number of observations, you just have so much freedom, like nothing. So how to predict yi has nothing to do with other observations, because if your goal is to just make your prediction as accurate as possible, then to make sure your prediction error is as small as possible, the best you can do is just to set each mu I equal to y. Yeah, because for prediction purposes, we will use mu I hat as our predictive value for yi. Does that make sense? So basically, if we go down here, if we go up here, so what I mean is that for prediction, using the model, your best guess is use your estimated EYI as a predictor for YI. So your YI hat is basically your mu I hat. Okay, and depending on how you get the mu I hat, if it's the GLM, then it's just G transpose Xi transpose beta hat, if it's the GLM. If it's just the saturated model, you would use YI. By saturated means that you cannot have more parameters than this one, because once your parameter number is larger or equal than n, because n is your data points, right, number of observations, then you basically exhaust all the possibilities. You can just use yi to estimate itself, to predict itself, because there's no constraint.
Okay, I know this is kind of a dumb question, but like you have the mu n parameters, okay,
Yeah.
one for every observation, and
Yeah.
then you want to evaluate a new point that's not
No, we're
that.
just talking about predicting the training data. It's just
Okay,
so if you use the
okay,
machine learning language, it's the training error. So
okay,
once you have a saturated model, the training error will for sure be 0.
got it.
Yeah,
Okay,
but so far this class didn't talk about anything about training versus testing. So that's the thing about like the classical statistical inference, which is that, okay, given your training data, you want to know how good the model fitting is good enough, using the likelihood, using the tests to guide you. Because if we talk about this deviance, there's no way you can beat the saturated model in terms of likelihood or training error. So I think intuitively on the training data, the larger the likelihood corresponds to the smaller the training error. So there's no way you can beat the saturated model. But we still hope that their difference is small enough so that we can go with GLM instead of saturated model. So, the good thing about this idea is that you are trying to evaluate whether their differences is bigger than the sampling error, the sampling uncertainty, given our model assumption. Like it can be Poisson, it can be Bernoulli, it can be Gaussian for the random structure. The random structure is what we assume for the randomness. So we're basically evaluating the differences of the two models compared to the assumed randomness. If it's within the assumed randomness, then we think, oh, their difference is not significant. Then I go with GLM. So that's the idea. So we don't need to use the test data to help us because we assume the randomness. But in machine learning, when people use the test data, what you free yourself from is that the assumption. So you don't need to make explicit assumptions as we make here. You're just fitting the data, use whatever complex model, and then use the test data to tell you whether you have overfitting or not. So it's a very different philosophy if you think about it. So machine learning is more like data driven, more based on the data. And this classical inference is for more about what we assume, more about our assumption. But you see that it has its use when your sample size is very small. So if you don't have so much data to allow you to do training test splitting, because you may just have 20 data points and you do the split, you have fewer for training, right? If that's a thing you don't want to do, then using assumption to kind of compensate your small sample size is the logic, is the philosophy here. Yeah. Yeah, I hope that makes sense. But it's a very good question. So I think traditionally, there are two ways of thinking, the statistical thinking and the machine learning thinking. So I would strongly recommend that there's a paper for like so I can send this to the course Brew Learn later, which is, maybe I can write it here, somewhere here. So which is something called, by this paper by Leo Breiman, which is a very classical paper. I think it was from maybe 2004, if I'm right, or 2000 something. Yeah, 2000, early 2000. So this paper is called The Two Cultures. Yeah, so this paper, when it was written, it actually stimulated a lot of discussion in the statistics community, because Leo Breiman, he passed away, I think 10 years ago, more than 10 years ago. But when he was a professor at Berkeley. He was in the statistics department. And at that time, the statistics culture, even for now, is still very model-based. It's focusing on the model like the ones we talk here. But he was advocating the machine learning culture in this paper, saying that if our goal is to do prediction, then we shouldn't be afraid of having a very complex model, many parameters. So I think this paper stimulated this discussion about which is our focus, inference or prediction. So that's why in the first lecture, I remember I said that for this class, our goal is more on the inference. We try to make sure that we can understand the model parameters, justify the model, then use the model parameters to make some story out of it. And I think this is what many people do in social science, especially if you want to say something has an effect on something, right? But prediction is not your primary concern. Yeah, so I think differentiating these two things is very important. But just to clarify, this paper was trying to advocate machine learning because at that time, machine learning was kind of ignored by statisticians. Yeah, but I think now the trend is different. So anyway, so yeah, that's a very important clarification. So in this class, so far, we're only talking about training data, no test data involved yet. And all right, so what's next? Let's continue. So let's use this log likelihood formula to write down the deviance, okay? So the deviance, I will just write it out. It's just 2 times this thing using the saturated model over minus 2 times this thing using the GLM. So essentially, I will just give you the answer. It's actually 2 times the summation I from 1 to n yi log yi mu I hat. And this mu I hat is from the GLM plus ni minus yi log ni minus yi ni minus mu I hat. That's it. This is the deviance formula for group data logistic regression. And as this is a likelihood ratio statistic itself, we know that asymptotically, under the null hypothesis, the null hypothesis here is that GLM, basically GLM is the true model. The simpler model is the true model. Under this null hypothesis, this deviance statistic will follow a chi-square distribution whose degrees of freedom is the difference in the number of parameters between saturated model and GLM, which is n minus p. So that's the deviance statistic. And you can think of it as a replacement for the, how to say, mean squared error. It's actually the mean squared error used for linear model. Actually, is it a mean square error? I think, okay, sorry, I should make it more explicit. It should be the sum of squared errors, the SSE, and we need to divide that by the sigma square hat, right? So that's the thing we talked about in the linear model part about the variance estimate. We need to scale that. And then, but roughly speaking, it's analogous to the mean square error, subject to some normalization, some multiplication of factors. So the intuition is that when you use generalized linear models, you need to talk about deviance. But if it's linear model, we typically talk about mean squared error. All right. Any questions before we continue? That's the first thing, deviance. The second goodness of fit statistic we'll introduce is called Pearson's chi-square. Oh, by the way, connecting this to what we talked in the beginning of this class are the 3 ideas. This deviance is related to the likelihood idea, using the likelihood to do the test. Pearson's chi-square statistic has some close connection to the score statistic for the linear model. But here we are not going to prove the equivalence. We'll just give you the general idea behind Pearson's chi-square statistic. So as some of you may know, Pearson is one of the founders of statistics more than 100 years ago. So that was the time when statistics emerged as a discipline. So the idea is very intuitive, I would say. So the idea is that we're interested in comparing the observed value for the ith observation minus the expected value for the ith observation under some certain model. We take the square difference as we always do, right? Because the square difference has no sign. If we don't care whether it's smaller than or bigger than, we just care about the absolute difference, then it makes sense to square it. But then again, we wonder this difference, if we want this difference to be, how to say, invariant to the expected value, because it's possible that if the expected value is bigger, then the difference tend to be bigger. So it's kind of a normalization idea. That is, we scale it by expected value of I. And then we take the sum over observations. This is known as the Pearson's chi-square statistic. Okay. So essentially, for specific to the group data logistic regression, what the Pearson's chi-square statistic looks like is actually very interesting. So the observed is of course the yi, but also we consider the other end. So in group I with ni observations, so let's say in group I, we have ni observations actually. And out of the ni observations, we actually have yi observations as 1 and ni minus yi observations as 0. So therefore, for the group data, when we use the Pearson's chi-square statistic, we actually consider the ungroup data as our observations. So in this group I, there are yi ones, ni minus yi zeros. So we will use those as our observation, and then we consider the expectation. So that's how we're going to do. So essentially, this statistic can be written as I from 1 to m, and this I is still for group I. But within each group, for the yi ones, their expectation is the mu I hat from GLM. That's how we expected yi to be, square over mu I hat. And also we consider the zeros in this group. And there are ni minus yi zeros. And the expectation of that is ni minus mu I hat zeros. And again, we take the square of the two. And the expected value is ni minus mu I hat. Okay, we take the sum. So this is what we call the Pearson's chi-square statistic for group data logistic regression. And interestingly, asymptotically, when the sample size goes to infinity, under the null hypothesis, also GLM is the true model, It follows chi-square distribution with m minus p degrees of freedom. So asymptotically, it's equivalent to the deviance. So that's what we just said. Asymptotically, the score test is similar to the asymptotic equivalence of the score test and the likelihood ratio test. Okay, so something you might have learned about the Pearson chi-square statistic is that I don't know how many of you have heard about the Fisher's exact test. So for that kind of problem, if you want to know whether two factors are independent or not, you can also use this approach. So in that case, your expectation will be under the independence. Assuming the two factors are independent, then what will be the expected counts if you have two factors, each with two levels, you have a 2x2 table, you have 4 entries in the table, then you can calculate the expected values of the 4 entries under independence. And these will be your expected value. And the observed 4 values will be the observed values. Okay. Any questions before we continue? So we introduced two goodness of fit test statistics, deviance, Pearson's chi-square. And our goal is to assess whether the fitting of the model, of the generalized linear model, is good enough. Is it good enough to be considered similar to the saturated model? So we are happy with the fitting. Okay, so in this case, I think Alex at the end of lecture last time asked a very nice question about whether we're looking for different things when we say goodness of fit test versus the inference of beta. Exactly, we do. When we say goodness of fit, we want the model to fit well. So we compare the GLM to the saturated model. But the next topic, when we talk about inference of beta, in GLM, when we talk about this, we try to know whether beta is 0 or not. Then the model we compare GLM against is the null model, where beta is 0. So we do have different targets, different comparison. Okay, so what do we do with the inference for beta? And for this, what we have about the optimization, right? You may wonder, why do we bother to derive that iterative reweighted least square algorithm? Because now we have many ways to do the optimization. Optimization seems no longer a problem with computer. Why do we need to derive that and try to find this iteration based on weighted least square? Here is the reason. Now you can see with that argument, inference of beta becomes feasible. Okay, so our idea is to use beta hat. So if we have this null hypothesis, beta equals 0 versus alternative, beta is not equal to 0. If this is what we want, then the first idea, remember, if you want to do Wald test, right? Wald test, how do we do? We need to have beta hat transpose the inverse of the variance of beta hat times beta hat. We need to do this. And the variance may have some plug-in if there are unknown parameters. But basically, once we have the model fitted, we have beta hat. That's the end result, the target we want to estimate. How about the variance term? Well, here it should be a covariance matrix P by P. So the question is, what do we get? How do we get this variance covariance matrix? So we can do the Wald test. And then the IRLS helps us. So if you recall, in the IRLS, we have this update. Say we are in the kth iteration and we want to update the beta hat to be the k plus 1 value. It's a weighted least square, x transpose wk, x inverse, x transpose wk, zk, right? And we give the z a name. Remember, it's called what? It's called a working dependent variable or working response. So the zk has this formula, x times beta hat k, the current value, the linear predictor given the current value, plus this additional terms as a linear approximation. So y1 minus mu1 hat k, the current mu1. times G prime link function derivative at mu1 hat K. That's for the first observation. Yn minus mu n hat K G prime mu n hat K. That's the Z hat. Okay. So you can imagine, right? Once you have convergence, everything stabilizes. Beta hat stabilizes, mu1 hat to mu n hat stabilizes. So upon convergence, we would just use the stabilized version for everything. So once mu hat, beta hat, and mu hat are stabilized, Z is also stabilized. So therefore, we can write as mu hat as X transpose W X inverse X transpose W Z, because W also stabilizes. Okay, so in this case, if we use this end result from the convergence from the iterative reweighted least square, then we can have the variance covariance matrix of beta hat as, so everything here is considered to be fixed. Random variables are only in Z because Z involves Y1 to Yn. These are random, but W is only about parameters. And once we assume that upon convergence, the parameters are the true values, so that's the approximation we do here. We don't consider the parameter estimates randomness. We consider them just to be parameters. Then the randomness only in Z. Then we have, basically, it's this left matrix multiplied to Z times variance of Z times the transpose of this matrix. That's what we do for the variance formula for the matrix form. So it becomes just variance covariance matrix of Z, and this is n by n. So this is P by P, this is n by n, times the transpose of this whole thing. And W transpose is itself, X transpose becomes X, and this inverse, as it's a square matrix, it stays. Okay. All right. And then don't forget that we have actually this property, which we talked about in our last lecture. You can go back and check if you don't remember it anymore. That is, this variance covariance matrix of Z is W inverse. So we actually have, remember, W is a diagonal matrix, and each entry, diagonal entry WI is 1 over the variance of ZI. We actually have that derivation. So with this, then you see we have some cancellation. This W and this W inverse get canceled. So we have X transpose WX in the middle, which can cancel one copy of the inverse here. So then we get X transpose W X inverse. Okay, so if we assume that the randomness is only in the Y and the parameters are the true values, that's what we get. So once we have the true parameter values, that's what we get. But of course, W is unknown, right? So when W is unknown, we need to plug in the parameter estimate for W because true value is unknown. So therefore, in practice, we do plugging. We have the variance hat, beta hat. So it's the estimated variance covariance matrix. And we use the estimator for W, X transpose W hat X inverse. That's it. Okay. And for linear model, let's go back to the special case of linear model to help you understand this whole thing. So in the linear model, special case, linear model, you see, for linear model, what we have for Z is actually Y. Because for linear model, there's no need for the link function because linear function is just an identity function. So there's no need to do that transformation. And in fact, if it's a linear function, linear model, G is just the identity function and its derivative is just 1. Okay, so its derivative is just 1. So basically, let me just write it. Let me see. Linear model x beta hat plus, let me still use the same thing so you understand what I'm saying. Y1 minus mu1 hat. I dropped the iteration iteration index mu n. And this G, so G function is just Gx is just x. It's just the identity function. Then the G prime is just 1. Okay, and we know that x beta hat for linear model is just mu hat. That's what we have. It's the predicted value for y1 to yn. So therefore, you have it as mu1 hat to mu n hat plus this thing, y1 minus mu1 hat, yn minus mu n hat. And then you have it just as y. It's just y1 to yn. So z is just y in the linear model. The working dependent variable reduced to just the actual response variable is the y dependent variable. So then you see, when you have that, then this w, right? W inverse used to be the variance of z. So here in this case, the w inverse is the variance of y. Okay, and the variance of y in the linear model is what? It's the same sigma square appearing in the diagonal line, right? Every yi has the variance as sigma square from the random error. So therefore, you see w hat, if I put a hat here, is just 1 over sigma square hat, 1 over sigma square hat to 1 over sigma square hat. That's the w hat. And then what is this x transpose x inverse? So you see that then the variance hat, estimated variance of beta hat as x transpose w hat x inverse, because this w hat is just diagonal with the same entries, 1 over sigma hat square. You can't get out of it. So I will actually have sigma square hat times x transpose x inverse. And that's exactly the formula we have for linear model, if you recall, for the variance covariance matrix of beta hat. Okay, so this is just to show that linear model is a special reduced case for the generalized linear model about the variance covariance matrix. And for generalized linear model, we're going to use this formula. And this formula, this W hat, will be the output from the last iteration of your IRLS, the convergence. You will take this W hat matrix out of it and then plug it in. And then to get this variance covariance matrix estimator of beta hat. Okay, and then we get Wald test statistic. So just same as before. So nothing special. We just put this back in here, put it back here, and then that's how we gonna do. So then I'll just write it down. Wald test statistic would just be beta hat transpose. This variance hat, variance covariance matrix we have over there, beta hat, inverse, beta hat, right? And if we put it here, if we put this inside, it's what? It's basically this beta hat transpose x transpose w hat x, the inverse and this inverse gets canceled, right? Because here we have the variance as the inverse, and now we have the inverse of the variance. So then the inverse is gone. times beta hat. That's it. And then for this Wald's test statistic, under the H0, which is beta equals 0, asymptotically, this converges to a chi-square distribution with p degrees of freedom. And here we are comparing this model, GLM, which has p parameters, with a null model, which has beta set to 0. So the null model has p fewer parameters. That's why the difference in number of parameters is p. Okay, so that's the Wald test. Any questions? Let me just label this as 1. Wald test is the first option for inference of beta. And if we continue, second option, which is the second idea, we give you likelihood. Okay, likelihood ratio test. And once we have the deviance available, then we can actually do this comparison. So in the likelihood ratio test, for the Wald test, I have to be specific. I only talk about this whole beta vector is 0, but I didn't talk about what if a sub-vector is 0. Sorry, maybe I should talk about that. Yeah, let's hold it for a little while. Maybe I'll just add something here. So what if the null hypothesis is that if you write beta as 2 parts, beta 1, beta 2. Beta 1 has P1 parameters, beta 2 has P2 parameters. What if this is the case? And if your null hypothesis is just about beta 2 being 0. I think this is more often in applications, right? You have many covariates, several covariates, and you are interested in whether a particular covariate has effect 0 or not. If this is the case, and we know that P1 plus P2 equals P. If this is what you're testing, then your Wald statistic should be this. Beta 2 hat transpose times the inverse of just the variance covariance estimate of beta 2 hat inverse times beta 2 hat. It should be like this. So therefore, what we need is this, how to say it. So basically, what we need is to get this sub vector beta 2 hat. What is its variance? So that's the thing. So what this will mean, it should be equal to, if I write this variance hat of beta hat, this P by P inverse, if I write this variance hat, beta hat inverse, okay, if I write it as a block matrix, so if I call this V11, V12, V21, V22, so this V22 is P2 by P2, the lower block, then what I mean here is actually this part. So I will put this V22 in here as this middle thing to multiply to. So because it's denoted as the inverse of the variance covariance matrix of beta 2 hat. But what we actually mean is that we need to take this component instead of just calculating the variance of beta 2 hat as a block diagonal of this variance beta hat and then inverse. So I'm just saying that if I have variance hat, beta hat, written also as a block diagonal, C11, C12, C21, C22, if I write it this way, then V22 is not equal to C22 inverse. That's what I mean. So it's like you take the whole inverse, this is the inverse of the whole thing, and you pick this block instead of just taking the C22 as the variance covariance and take the inverse. Because if you do it this way, you kind of ignored the other beta 1 hat, you also need to estimate. That's the reason. Because this thing will be affected by this whole estimate, not just the estimate of beta 2 hat. Okay, so that's the Wald statistic if you want to test a subvector. So coming back to the likelihood ratio test statistic, if I'm still interested in the same null hypothesis, beta 2 equals 0, then I'm comparing two models. So here the constraint model, the smaller constraint model, is that you only have P1 parameters. You only have beta to estimate P1 parameters versus the full model. Full model means the GLM with beta as the whole thing. And then you have P parameters. You compare these two. So ideally, you know that you want to have the likelihood ratio test statistic as this -2 times the log likelihood under the constraint model, where your beta 1 will be estimated by its NLE, and beta 2 will stay as 0. Minus the full model is that your whole beta will be estimated. Probably I'll put it this way. Beta 1 hat 0. So this 0 is P2 dimensions itself. So I'm basically using the P2 dimensional 0 vector to represent beta 2. Okay, that's what we do. But both are GLM. It's just that for the first one, it's a constraint GLM. We only estimate beta 1 hat and setting the beta 2 to 0. Second is an unconstrained GLM. You estimate everything. Okay, and then what do we do? If you already fit those two models, so this is fitted model 1, and this is from fitted model 2. You fit two GLM models. So one thing we can use in practice, once you fit each model using, say in R, you have the GLM function to fit each model. If you do that, then you can actually use the output from the model fitting using the deviance. So the deviance 1, you see, is actually -2 log likelihood of this fitted model beta 1, 0 minus the log likelihood of the saturated model, if you remember. It's the mu hat saturated model, where each mu I hat is yi. While for the fitted model 2, the deviance you get from here is -2 times the log likelihood of the beta hat from the GLM minus the log likelihood from the saturated model. Okay, and then you see the log likelihood from the saturated model is the same thing. They can cancel each other. So therefore, you see that it's basically, if I put this back in, it's just the deviance 1 minus deviance 2. I just need to take the deviance output by each model fitting and put them here. And you know that deviance 1 is expected to be bigger than deviance 2. The reason is that deviance 1 is measuring the deviance of this smaller constraint model from the saturated model. And their difference is expected to be bigger than the difference between this unconstrained GLM and saturated model, because this unconstrained GLM is more complex than this model. So it should be closer to the saturated model. So that's why we expect D1 to be bigger than D2. And their difference is exactly the likelihood ratio test statistic we need. Okay, and in this case, under the null hypothesis, asymptotically, it's chi-squared P2 degrees of freedom. Okay, so that's the inference for beta. So just to summarize, for inference of beta, we are typically interested in answering this question. Does one covariate have any effect on my response? So on the linear model, in the linear model, the effect on the response is directly on its expectation with no transformation. But for generalized linear model, because of the link function G, when we talk about how the effect of a covariate, once it increases by 1 unit, how does the coefficient, say beta J for the covariate J, is affecting the expectation of yi, say mu I, you need to consider the link function, where how it amplifies effect or reduces the effect. That's the thing we need to be careful. Okay, so that's all I want to say about the inference part, about the effect. And goodness of fit is just to assess whether overall the model fits good enough. Okay, whether it's good enough compared to a saturated model and whether we should use the model. So the logic is that in practice, we will first do, maybe I'll write here. We first do goodness of fit check to see whether the model is reasonable. Model reasonable? If the answer is yes, then we go to next step. We do the inference of a certain beta J to tell a story about the covariate J. So that's how we do it in practice. But sometimes when people use generalized linear model to tell a story, maybe they skip the goodness of fit part. Then this is the problem. You may not really know how reasonable the model is. If the model is not reasonable, then we don't trust the inference result based on it. Okay, so that's almost for today. So for maybe I can just say a little bit thing about the next lecture. So which is about other link functions for logistic regression. So now we try to return to logistic regression again. So in logistic regression, using binary data, so yi 0, 1. So this is like the individual data, no grouping, right? Recall that we have the random structure as just yi independently following Bernoulli with mean parameter pi I. And the systematic structure is G pi I as xi transpose beta. This is what we did. So when we say logistic regression, we have a specific form, right? So for logistic, we have G pi I just as the logit pi I, which is the log pi I 1 minus pi I. This is what we have. But I remember at that time, there was a question I think asked by Chen Xin in our class about why we specify G in this way. There might be other ways that can do the same thing. So what we only need is that we need a G function to help us map the domain 0 to 1 to the real line. That's what we only need. So there are other options out there. So one possible option, for example, is that we can specify G pi I just as the inverse of the CDF function of standard normal distribution. So where this phi is the CDF of standard normal. And you know the CDF function has domain 0 to 1, has range 0 to 1. So it maps the real line to 0 to 1. So its inverse maps this 0 to 1 to real line. So it makes sense to use it as another possible link function. So this one actually gets a name. It has a name. It's called probit regression. And it was once used in history. And later, the consensus is more about using the logistic instead of the probit. I think one explanation is the canonical link function. That's what we did from the generalized linear model theory. But the probit regression was there. And so in the next time, we will try to give you another interpretation about how do we consider this binary response regression problem using the latent variable formulation. So it's another way to interpret this whole problem of the binary response regression by linking it to the linear regression. So yeah, that's all for today. So then I'll see you on next Monday. Well, we'll see what the university says about the instruction policy next week. So anyway, so if you have any questions, you can stay in the Zoom meeting and you can ask your questions.